Welcome everyone to the first top colloquium of this semester, which is going to be slightly different than the other colloquia. We're going to hear from 6 PhD students, 2 from each of the departments involved in top. They're local, so this is a meet yourself event. But throughout the rest of the semester, we'll have a few more canonical colloquia, including one for this year top research prize, which has not been announced yet. And there are, as usual, also lectures promoted by the various top initiatives, some of which will include computational workshops in dates to be defined, but this slide is pretty much summarizing this semester in top. Also, if you have not done it and systematically for all of these other events, please remember to sign up on these sheets that help us getting funds from top. Oh, and good. Oh, and well, without any further delay, I think we can switch directly to the content of today. And the first speaker is going to be Vikram.
All right, I'm assuming everyone can hear me. Cool. All right. As Matthew said, I'm Vikram Manikantan. I am a astronomy PhD candidate working with Vasilis Pascalidis and Gabriela Bazzola. And today I'm going to tell you about my research on coincident multi-messenger bursts from eccentric supermassive binary black holes. So we expect supermassive binary black holes, abbreviated up top left, to be ubiquitous and the ubiquitous product of galaxy mergers. So when galaxies merge, we expect their supermassive black holes to eventually come together in spiral and form a binary. We also expect these to be extremely useful multi-messenger sources. We expect gravitational waves from their in spiral, and accretion onto each of the horizons should generate electromagnetic emission across the electromagnetic spectrum. This makes them great for tracing the large-scale structure of the universe because they trace galaxy mergers. And multi-messenger emission from these systems should help provide a fundamentally new probe of H0 and the universe's expansion. However, there's a catch. At the moment, supermassive binary black holes are extremely difficult to confirm. The gravitational waves they emit are low frequency and currently out of the range of pulsar timing arrays and the laser interferometer space antenna. Sorry, not yet, but they will eventually be observed by the laser interferometer space antenna in the 2030s. Currently, there are no supermassive binary black hole candidates for the EHT to observe. This might change with the next generation Event Horizon Telescope. So at the moment, we rely on electromagnetic observations to help identify supermassive binary black hole candidates. So these are usually blazar type objects that are variable that can be explained by the presence of a binary. However, at the moment, they are just candidates. And so we turn to simulations to help provide smoking gun electromagnetic counterparts and theoretical models to help identify these supermassive binary black holes in nature. There's a pretty simulation. And so we, in our simulations, evolve the equations of ideal MHD. We also evolve the space-time around these objects to properly model the fluid flow onto the horizons. And in this study, for the first time, we look at orbital eccentricity. And this is a timely study because, as you can see, these recent studies of long-term evolution of binaries have suggested that eccentricity is meant to be, or supposed to be, fairly ubiquitous for supermassive binary black hole mergers. And so the goal of this work is to understand what eccentricity does to observable electromagnetic signatures of these black holes. And so in our work, we look at an eccentricity of 0.3 just as a point of principle. And you'll notice throughout my simulations and plots, I use the unit M. And in the spatial domain, you can think of M as about 10 to the 7 kilometers for a 10 to the 7 solar mass binary. You can ask me questions about that later. Okay, cool. So this is our initial simulation setup. In this cavity here are 2 black holes. You can't see them at the moment. Surrounded by that is a circumbinary disk. We're looking at the XY plane of this system. And so we're looking face down into the binary orbit. And the brighter colors indicate higher fluid density. So I can let this play. You'll notice there are tidal streams falling in from the inner edge of the circumbinary disk. They circularize around each of the black holes, and eventually they will accrete. You'll notice the black holes are doing this speeding up, slowing down thing. That's the eccentricity. Okay, awesome. All right, so the basic picture of these simulations is that magnetized gas accretes onto these horizons, and eventually they will launch jets. And so here on the right, what you're looking at is the XZ plane. So now we're looking face on at the system, or at a slice of the system like that. We see the two black holes here near the center of this image, and vertically extended from both black holes is the relativistic jet. The colors indicating the fluid magnetization. So the brighter areas indicate higher fluid magnetization. These white streamlines are the large scale magnetic field. And you'll notice that the magnetic field is ordered within the jet regions. But let's not forget what the point of the study was, is to understand electromagnetic emission from these systems. And so we can take a look at the mass accretion rate onto each of the horizons. All right, some of the lines are not showing up. As you can see, those are missing, but we'll move through it. The basic picture is that with time, we see the accretion rate oscillate with the periodicity. And so the natural question to ask is, what is this periodicity? So we perform a fast or a Fourier transform, and we notice that this periodicity is actually at the orbital frequency. And so that's our first key result. And you can also think of this periodic accretion as an analog for UV and X-ray emission from the inner regions of the accretion flow. All right, so the next question we might ask is, what is happening with these jets? Is there some sort of measurable electromagnetic signature from these jets? And so we perform a synchrotron radiative transfer within the jet regions to understand what that might look like. And so what you're looking at here is a spectral energy distribution of our object with respect to time. So here on the y-axis is the emission frequency, and it's time in hours for about a 10 to the 7 solar mass binary. You'll notice that the colors indicate the specific luminosity, and that there is a natural break here, which indicates the peak of our synchrotron spectral distribution. You'll notice these fringe-like structures, and those are peaks in this synchrotron emission that repeat in time, these fringe-like structures. And so we can ask the same question as before. What is the variability or the periodicity associated with this signal? So we perform a Fourier transform once again, and we notice that this signal is also modulated at the orbital frequency. And so that's the second key result from this work. All right, so last but not least, we can also ask about coincident multi-messenger observations. So we talked about electromagnetic observations. Now we can talk about gravitational wave signals. And so gravitational waves from eccentric binaries will have this burst-like structure in the amplitude of their gravitational wave. We can also ask about the total jet power. This is a point in luminosity from the system. And we notice that that also has a periodic structure. And the synchrotron emission, integrated for the optically thin frequencies, as we just saw, has a periodic structure in its emission. And so there are gray lines along these peaks. They're not showing up, so you can imagine them for me. And what you'll see is that they're actually all aligned. And so what our key conclusion from this work is that there's actually potential for coincident observations of electromagnetic and gravitational wave bursts from these systems. And so, okay, I'm gonna leave you with the conclusions that I just went over. And the most exciting thing is that I'm hopefully gonna start applying these models to actual observational data. Scary stuff. But I'm really excited to look at it and actually see whether these things really exist, which I'm sure they do. Of course, they do exist. Sure, yeah, any questions? Thank you.
Great, nice talk. And yes, I'm sure they exist. Whether or not we found any of them, these are the right candidates. That's another question. But my question relates to that comparison. So, how long are you able to run these calculations for? And from your emission plots down there, it does look like it's achieved a pretty remarkable steady state. But I guess I'm surprised that it's that easy to do.
Yeah. So the limiting factor for our simulations is the simulation runtime. So these took me in the order of like 6 months. on Texas Advanced Computing Center, TAC. And so that's the limiting factor for how long we can study these objects. Another limiting factor is the eccentricity. The higher the eccentricity, the quicker these objects inspiral and eventually merge. And so finding that sweet spot between putting them far enough apart that they have enough time to evolve and not running the simulation for too long is what we're dealing with right now. And yeah, they have actually reached a steady state, as you mentioned.
So, but you're keeping the binary fixed, or no?
No, this is a complete evolution from first principles. So we initialize the space-time and we let Einstein's equations do the work. And so this gravitational wave emission is the gravitational wave emission that you would see from these objects.
So how many orbital periods are you able to? I guess I'm surprised you can really get a steady state if the orbits are evolving that quickly.
Yeah. So the total simulation is about 13 orbits, and we say that the fluid reaches a quasi-steady state after about 5 orbits, which is generally in agreement with previous works.
Not for the non-GR case. Is it different?
Yeah, I would say it's slightly different. I mean, in the non-GR case, let's see. So the way we define, let me tell you about the way we define steady state. The way we define steady state.
Maybe this is good.
Okay, yeah.
We'll take this offline.
Yeah.
Let's say maybe we can take another quick question while Tyler, like while we try to switch speakers. There was one over there. It's the first hand up.
Yeah. So how do you choose the initial conditions? Do you know something? Just speak to us about initial conditions. What?
Yeah. So
plausible.
Yes, initial conditions are an open topic. There are some well-known solutions for the accretion disk, and so what we use is a power law solution for the accretion disk. The initial data is we solve for the initial data using a spectral method. I'm not exactly sure, but it's a well-tested and well-known method. There's well-known faults with the initial data. It's a thing called junk radiation that happens in our gravitational wave emission. But like I said, after a few orbits, this stuff all settles down. And so we can fairly confidently say that initial conditions don't play a huge part in our results. But I would say that we can still do some more research into the role that initial data plays.
So by that, you mean you've tried many different initial conditions and you get the same steady state?
So I haven't personally, but this is a pretty advanced field in the sense that there's been hundreds, if not thousands, of simulations of accretion onto black holes. And these are well-established initial data.
Let's thank Vikram again. Our next speaker is Tyler from LPL.
Hi, I'm Tyler, first year graduate student at LPL. My advisor is Joe Giacalone, and that title is really long. So I'm kind of just interested in particle acceleration in plasmas in the solar sphere, heliosphere. There's kind of like 2 basic flavors of that, and those are like cosmic rays, like something out of the solar system, like something from a supernova or something, and energetic particles, solar wind particles, and something that's kind of unique about both of those is they have these really kind of high energy tails and stuff with a mini MeV. And they're mostly protons. They're all charged particles. And so it's sort of kind of interesting. You're always trying to find out, okay, how do these particles get to such high energies? Why are they so high energy? What do we do about it? And the conclusion seems to be, or so I've been told, is that it's due to shock acceleration. Shocks are pushing these particles and accelerating them. Just some quick kind of examples. Does this have a laser on it? Ooh. So it's just like kind of some examples of heliosphere shocks, right? You have the solar wind termination shock. There maybe is a bow shock. Joe told me the other day, maybe not. And then there's also, the bow shock in our magnetosphere. Maybe these are the one that's very close to home. I'm kind of primarily right now focused on the termination shock. So like something at like 100 AU and stuff. But when particles interact with this, they should be accelerating. Some maybe relevant research missions to this are New Horizons. It's way out there already at like 58 AU. And so they extended the mission. There's some plasma instruments on there, some particle detectors on there. And so maybe 4 or 5 years, 5 to 8 years, I wrote, it should cross the termination shock, and we'll have some measurements of the energy spectra. And then IMAP is launching soon to L1, and that's going to get some measurements of the spectra at 1 AU. And so hopefully we can kind of establish the correspondence between 1 and 100. To be a little interesting. Why on earth would anyone care about cosmic rays? I think they're neat, but they do affect things. Ionizing radiation, if you're in space, you put any research mission out there, any humans out there, you're going to be exposed to radiation, particulate ionizing radiation. It's going to break your electronics. It'll give your astronauts cancer. They don't like to do that. And so in order to design a rad-hard system, you need to know you need to know what your environment's going to be, and you start getting into this loop of, all right, I'm designing to be rad hard, I'm evaluating a rad hard design, and if you're going through this loop too much, you're just spending money. And so this is really getting to the bottom line of everyone's research mission. What are the energies of these particles? How can we shield them? And then, so what am I doing? Lots of things, but we're trying sort of a soft Monte Carlo brute force method. You kind of take the plasma, the field and the streaming velocity as a given, and then you run little test particle orbits through the field, and you establish a boundary. You have your jump conditions here, and you give it some compression ratio, and you can just try and integrate the orbits as it traverses through the field, right? You just have to solve the Lorentz force. And then if you want to add a little wrinkle to it, you start to inject, here's a PSD, but you can inject turbulence like in this inertial range, right? So it's like here, when you have that, like this is when the what do you call it? The Reynolds number is infinite, right? It's we're beyond all interest here. And then here it goes to 1, turbulence sort of ceases and stuff. So we want to live in this inertial range, and you can kind of inject some isotropic turbulence here at the boundary and see how that affects your orbit. And then you start to get an idea what the energy spectrum might be. So I've gotten most of a code and stuff. And so you can see we can integrate orbits so slowly, right? And we can have nice isotropic Komorov turbulence. It's a big circle. And so, it's there. I'm just kind of doing software engineering stuff at this point, trying to make it more stable. I want to get it containerized so we can put it on a big Linux box and actually take spectral measurements and stuff. But yeah, and obviously you can make it more complicated. You can add in a moving shock and stuff. But yeah, it just got here. That's all I got.
Are you using a Boris pusher, or what are you using?
Oh, I was doing just classic RK4 and stuff. I tried a few different tableaus, like butcher tableaus for it. None of them seemed any faster, any more stable. So I kind of just settled on classic RK4.
I would take a look at Boris. It could provide some benefits. So.
Yeah, is it faster?
In some circumstances.
Yeah, like fast.
So do you have a sense of what kind of numbers you're going for, the environment we're talking about? Have people looked at this before? Or has this just never been characterized before?
Oh, it's totally been characterized before. Voyager took I think 2 measurements, but 2 measurements from forever ago aren't amazing. But yeah, I think we're expecting acceleration. But yeah, I don't know. I got a lot to learn. It's a good question. I should go look that up.
How general is turbulent? Work for any kind of shocks? Or?
It works for plasma shocks. I put a lot of assumptions in it, right? I mean, this assumes ideal MHD, but I tried to make it kind of general so I could throw it at a couple other things. So yeah, it's relatively general as long as you can assume ideal MHD and nice isotropic turbulence.
That's a great point, though, because there's a lot of different, like you said, astrophysical shocks and bow shocks. So there could be a lot of other interesting.
Cool. I charge $50 an hour, so.
So let's think. Well, on the schedule it says, yeah. Oh, no, you're right. I am wrong. You are next. I'm sorry. You're right. So the next speaker is actually Ian.
Okay.
And when you have like 2 minutes left.
Oh, okay. Yeah. Okay. I'm Ian Matheson. I'm in AME, but aerospace and mechanical engineering. But Renew lets me pretend to be an LPL, so here I am. I'm working on the mean pole of the Hilda asteroids. The Hilda asteroids are the group that's in a 3-to-2 mean motion resonance with Jupiter. When we look at this picture of the XY ecliptic plane of the solar system, the Hildas are the orange dots. They form sort of a triangle with ends at the Jupiter Trojans. We're interested in the Hildas because they're observationally complete. We think we have recorded all of them down to about a magnitude of 15.7. And there are 3 principal groups in them: a collisional family of the asteroid Hilda, a collisional family of asteroid Schubart, and ones that are not in those families that I call backgrounds. So here, but again, XY plane, they form a nice, fun triangle figure in the XY ecliptic plane and the rotating plane. Rotating frame with Jupiter, they also have this nice, fun triangle formation. In the what I'm interested here is their mean orbit pole, where the orbit pole is the unit normal to the orbit plane. That is also the same direction as the angular momentum vector. So we're interested in the mean direction of the angular momentum of these asteroids because that is influenced by perturbations from the massive planets. So if we understand all of the massive planets, then they should hopefully perturb the orbits of this group into some understandable mean direction. And if it differs from what we see, if the mean direction we see differs from what we predict, there might be a planet we don't know about messing things up, or our theory is just wrong. So here, this PQ plane is a convenient way to plot the orbit poles of these asteroids. We can easily calculate the mean orbit poles of the asteroids we know. For these groups, the collisional Hilda family, which is the red ring, the collisional Schubart family, which is the blue ring, background Hildas, which are the green dots. But the question is, does that mean anything? So like I said before, haven't said actually, outside of mean motion resonances, the mean orbit pole under secular perturbations is very well understood to be governed by what I refer to shorthand as Laplace theory. And that theory matches observations fairly well for groups of non-resonant asteroids in the asteroid belt and in the Kuiper belt. Worked on that a couple of years ago. But the question is, for mean motion resonant asteroids which don't have that Laplace theory, can we still say that the Laplace pole is a decent description of the mean pole? So here I have plotted the mean poles of the collisional Schubart, collisional Hildas, and background Hildas. Got the Laplace pole, which is the L, the Jupiter pole, J, and the invariable pole of the solar system, I. And I've got some fun statistical ellipses. So I can say that right now it looks like, statistically speaking, the observed mean poles of these Hilda groups are pretty close to the Laplace pole. And a million years from now, just propagating and rebound, they still look to be pretty close. On the left side, the JL dot is pretty close to the center of these statistical ellipses. On the right side, the JL dot is also pretty close to the center of the statistical ellipses, except for B, which is the background Hildas that have moved away. And so the question is, we see this we see this overlap, but is it statistically significant? So we propagate these groups over a million years. We propagate clones of asteroid Hilda and clones of asteroid Schubart and clones of a background object over a million years. And we do some statistical bounds to say, is the Laplace pole within these statistical bounds? And it looks like it is over 1 million years, but is that Laplace pole the best pole we could be comparing our observations to? We also want to compare to other convenient poles like the Jupiter orbit pole and the invariable pole of the solar system, which is the direction of the total orbital angular momentum of the solar system. So when we propagate some more clones and do some more statistics, we can say that it looks like the Laplace pole is a better fit than the Jupiter pole or the invariable pole. Here we see the median probability mass, a distance, the statistical measure I'm looking at, which I'm calling the median PRM, is smaller relative to the Laplace pole, 5%, than it is relative to the Jupiter pole, 7%, or relative to the invariable pole, 14%. But there's still a lot of statistical questions about what sample size of simulated objects we should be looking at, how long we should be propagating to get a good dynamical picture, etc. So there's still a lot of unanswered statistical questions of what's the best numerical approach to look at this question. And there's still a lot of unanswered analytical questions of, can we actually go into the disturbing function and derive a useful analytical prediction instead of hand waving and relying on this Laplace theory that is known to be not strictly applicable to mean motion resonances. And that's what I've been working on, and I'll take your questions. Yeah.
Yes, thanks for the great talk. Super out of my field, but I'm curious, if there were a planet 9, would it have any effect on the orbital poles of these asteroids?
Oh, well, you can make up a planet 9 that'll have any effect you want, pretty much. But the question is, are there reasonable planet 9s that could account for the differences we see between the Laplace pole and these mean poles? And there probably could be, but I don't know what their characteristics would be. Yeah.
Yeah, I was curious about how you define the background objects and.
So there, I download the list of Hilda asteroids from the Minor Planet Center, and I'm using the list of the list of collisional Hildas and collisional Schubarts that was made by a researcher in, I think, 2005, so quite a long time ago, and I don't remember the researcher's name offhand. But in any case, the Hilda and Schubart family lists are a little outdated, so there's some Hildas and some Schubarts contaminating my sample of background objects, but that would be a whole nother kettle of fish to identify these collisional families myself.
Yeah, I was just wondering almost the other way around, how many of your background objects are contaminating the samples and how that might affect the comparison to Laplace.
I don't think there are any background objects contaminating the collisional Hildas and Schubarts. The contamination goes the other way, and it is noticeable in the backgrounds. Yeah, you had a question on the right?
We have time if you want.
That's okay.
Any more questions? All right, thank you. Oh, thingy.
So, hello everyone, I'm Niranjana and I'm a grad student with Chris Klein. So, I'm talking about the work that we have been doing on estimating heating of solar wind observed by Parker Solar Probe. So, solar wind is a stream of charged particles, mostly protons and electrons, that is continuously streaming away from the sun. And in the plot here, the blue curve shows the fit to the observed temperature profile as the solar wind expands. And the green curve here shows the expected temperature profile if it were an adiabatic expansion. But we see that the observed temperatures are always greater than the adiabatic temperatures, indicating that solar wind is being continuously heated as it expands away from the sun. So what are the causes of this heating? So dissipation of turbulence and waves that we observe in the solar wind are the likely sources of this heating. And solar wind is weakly collisional. So wave particle resonance mechanisms like Landau and cyclotron resonance play a crucial role in this heating. So Parker Solar Probe, which was launched in 2018, has been orbiting the sun very close. And we use its observation to understand the solar wind heating near the sun. And here I show an example solar wind expansion heating expansion model that considers protons and electrons as two different fluid. And the quantities in the green boxes here are the heating rates. And this is what we intend to evaluate in our work. So solar wind has properties of both turbulence, and also it has a lot of majority of solar wind fluctuations have properties of Alfvén waves. So Alfvén waves are a fundamental plasma wave where a ripple in the magnetic field propagates along the magnetic field. So it's similar to a wave on a string. And Alfvén waves are characterized by this correlations or anti-correlations between velocity and magnetic field fluctuations, which we often see in the solar wind. So the plot here shows 20 hours of pure Alfvénic fluctuations observed in the solar wind. And these Alfvén waves could be triggered near the surface of the sun due to the photospheric motions of the footprints of these open magnetic field lines. And so solar wind is also turbulent. So here is an example turbulent spectrum of solar wind, where at large scales energy flows from scale to scale without damping. But once turbulent reaches scales of proton gyroradius or electron gyroradius, the wave particle resonance mechanisms are active and damp the energy from the turbulent cascade. And turbulence in solar wind is expected to be mediated by Alfvén waves. So Alfvén waves that are generated near the sun propagate outwards, and some of them can get reflected back towards the sun. And these counter-propagating Alfvén waves, they shear each other, producing Alfvén waves at smaller scales, which in turn produce Alfvén waves at even smaller scales. And the turbulent energy cascade keeps going to smaller scales. And due to the alphenicity, the cascade is anisotropic, so energy is preferentially channeled to smaller perpendicular scales rather than parallel scales. When the Alfvén waves reach very small scales, so at these small scales, they can damp onto protons and electrons by a resonance mechanism called Landau damping, where the waves interact with particles that are traveling with similar but slightly lesser velocity, can push the particles and eventually heat them. And to model this Landau damping, we use this cascade model developed in House et al. 2008, which considers this counter-propagating Alfvén waves and the damping to be damped by linear Landau damping rates. And the model solves this one-dimensional energy spectrum continuity equation and evolves this steady-state energy spectrum for a parcel of solar wind. And we'll discuss how it compares with observations soon. Moreover, in addition to all these Alfvénic fluctuations that we observe in solar wind, we also observe circularly polarized waves near the proton scales, and they manifest as these big bumps in the energy spectrum. And this is a spectrum of spacecraft frame circular polarization as a function of frequency and time, evaluated using wavelet transforms. And we see this dark red band corresponding to high circular polarization corresponding to the bumps here. So we can see the rotation of magnetic fields in this region. So these circularly polarized waves can interact with protons and electrons by cyclotron resonance and heat them in the perpendicular direction. compared to the Landau damping, which heats them in the parallel direction. So in our work, we wanted to estimate the heating due to Landau damping and cyclotron damping. So we do that by using this polarization as a criteria. So we evaluate this polarization spectrum. We identify region with high polarization and associate with waves. And the background turbulence produces this region of low circular polarization. And then we evaluate the turbulent energy spectrum in green and the wave energy spectrum in blue and red. And to the turbulent energy spectrum, we apply the model that I described previously. And when the model and the observed turbulent energy spectrum match very well, we consider that the model is accurate and evaluate Landau heating rate. And then to the distinguish wave energy spectrum, we use linear cyclotron damping rates, which we evaluate using linear plasma dispersion solvers and evaluate heating due to cyclotron damping. And here I show our results. So we plot the proton heating rates due to Landau and cyclotron damping. The cyclotron damping is in blue and red, and the Landau damping is in green. So we infer significant cyclotron damping, that is a lot of perpendicular heating, more than parallel heating, and it is consistent with the observed temperatures of proton. We see higher perpendicular temperatures rather than parallel temperatures. And here we plot the proton to total heating rate due to Landau and cyclotron damping. So the solid green curve is our estimate, and the blue curve and the blue shaded region is the empirical estimate by using solar wind expansion models, and they agree pretty well. So to summarize the work that we have been doing so far, we consider for the dissipation of two abundantly but distinct solar wind fluctuations, one Alpine waves and kinetic Alpine waves, and the other are the circularly polarized waves. So they live out in different regions in the wave vector space. So and we account for them, one of them by using turbulent cascade models and the other by using plasma dispersion solvers. And then we find that the heating rate that we estimate are in good agreement with the expected heating rates. And in my current work, we are trying to put this the dissipation of both these distinct fluctuations under the same model, under the same mathematical framework, by considering a turbulent cascade in both parallel and perpendicular directions. Thank you.
So could you provide maybe a little bit of a bigger picture of like what your results are really meaning? I mean, there's this model that exists, you're applying it to the sun.
Yeah. So the results would be like we did observe a lot of this perpendicular heating, right? So we do observe so in the plot here, in the orange curve shows the anisotropic temperature of protons, and we see a lot of perpendicular temperatures for protons, but we kind of expected maybe it is due to cyclotron damping of these waves, but we actually estimate and kind of provide argument for it. And also another interpretation that we could do, that cyclotron damping being the major mechanism and Landau damping being the minor mechanism, they could account for a lot of heating that of the solar wind that we see. Yeah, but again, this is a limited range of observations that I show in the plots. So there could also be other mechanisms that we need to care about. Yeah, so basically we are trying to figure out what different mechanisms could heat the solar wind at what different conditions and distances, and there could be a lot of mechanisms. Yeah.
Question? I have one. So the heating here can continue for several AUs, right?
Yeah, it can continue for, yeah. If
and
you
that
look, yeah.
will presumably change also the velocity at infinity of the solar wind particles.
Yeah, I mean, yeah, it's gonna affect the solar wind velocity until a long distance. You see, at least here you can see till 60 AU, and there can be heating till a long distance. Yeah.
just work something for my models.
Say the solar wind population changes considerably between, you start getting a lot of pickup ions farther out. So by 50 AU, you have and a lot of people are arguing that the pickup ions are what's doing the heating beyond about 20 or 30 AU and outwards.
Which is what's included in that Smith model.
Doesn't look like it's ever flat before 50 AU. There are no other questions.
I imagine that you have to assume some geometry of the solar wind.
Yeah, I think it's usually assumed
Spherically,
spherical,
symmetrically.
yeah.
Is that what you assume?
Yeah, we usually,
It's not. What if it is more two-dimensional? Would that solve that discrepancy? But maybe you know that it's actually pretty spherically isotropic.
yeah, I think we do know that it's more isotropic.
Could you go back one slide? We have gone over the poles and people have done at least
Right,
2D
but
approximation.
at large distances, does it remain spherical?
It depends on the solar cycle.
Ah,
Yeah.
Yeah. I mean, that's a solar minimum plot. So when the sun's nice and quiet, it's got this high speed in the poles and low speed in the equator. So it's two-dimensional like you. But during solar max, it's, I guess in some sense, isotropic is just very complicated.
Stochastic maybe is a better description.
Okay, so the dimensionality of the flow.
Maybe we
does
should
not-
thank our speaker in the interest of time.
All right, can everyone hear me okay? All right, I'm Sóley Hyman. I'm a fifth-year graduate student with Kate Daniel over at Steward Observatory. And today I'll be talking about how we're using a method that we've developed called PECCARY to probe the role of chaos in galaxy evolution. I'll also mention that this has potential interesting synergies with planetary dynamics. So if you're interested in trying to apply PECCARY to your research, please come up and talk to me afterwards because I'd love to talk more. To give a little bit of background, in galaxy dynamics, we think that one of the key drivers is transitions between different types of orbital families. So you've got periodic closed orbits, you've got regular kind of rosette orbits, you've got chaotic or more complex orbits, and you also have natural stochasticity or randomness. And as stellar orbits change between these different types, they can affect how different structures in galaxies like bars and bulges evolve. However, chaos is really difficult to identify, especially when you're comparing it with noise. These can often look very similar. There are various methods out there. You might be familiar with Lyapunov exponents. You might be familiar with surface of section maps or frequency analysis. These are some ways we can try to identify chaos in orbits. But what PECCARY can do that's very elegant and beautiful is that it can look at individual orbits. You don't need a divergence theory. You don't need multiple orbits to compare and see how quickly they diverge. It also can probe chaos on relatively short timescales compared to other methods. And it also can look at evolving potentials because actually the method itself, which I'll talk about in a slide or two, is agnostic to whatever kind of potential or even data you're looking at. So this expands what kind of questions we can ask in terms of galaxy evolution. All right, so PECCARY stands for Permutation, Entropy, and Statistical Complexity Analysis in Astrophysics, named after our beloved javelinas or calorificaries here in Tucson. It is a statistical method for sampling a time series. So you can have, it actually has its origins in plasma physics, which is a little bit of a good segue from the previous talk because they were actually looking at laboratory-based experiments and trying to look at turbulence and magnetic fields of like lab-based solar wind experiments. But what this method does is that it has this ordinal pattern sampling, I'll talk about that in a minute, of any sort of time series. So this could be X versus time, this could be radial velocity, radial coordinate versus time, this could be angular momentum. And you can probe and identify regular, complex, and stochastic behavior on many different timescales. All right, so how does this work? You've got some sort of time series and you extract points. You've got two parameters for how you do this. The first parameter is a sampling size, n. So it's basically how many points are you extracting out for a given pattern at a time. And so in this case, we have an n of 4. Second parameter is the sampling interval, which we call L, and it's how many points do you skip between each extracted point. So in this case, we've got an L of 3. So we're skipping over 3 points, or skipping 3 points to our next extracted point. And this overall gives us a pattern timescale. This tells us on what timescale we're like probing chaos or regularity in a time series. And then from there, what we do is we have extract those points and compare their relative amplitudes and order them. This is the ordinal pattern. We order them from lowest relative amplitude to highest relative amplitude by their index numbers. So in this case, the extracted points we have are 4, 1, 2, 3. That's our ordinal pattern. And then you scan along the data. So now we have 2, 3, 4, 1, 4, 2, 1, 3. You take all of those ordinal patterns and basically you've got, if you have 4 points, you have 4 factorial possible orderings of these points. And you create these pattern distributions. So if you have a random time series, so something like white noise, you expect to see all possible permutations of these patterns. And so you'll have a pattern distribution that's very close to uniform. If you have something like a sine wave, where you have these ramps up and down and peak and trough behaviors, you get very characteristic, very few distinct patterns. So right here, we've got those ramps up and down. And if you're really close up here, you can see a couple other behaviors from the peak and trough. And then in the middle, we have, for example, a chaotic time series, like an anon map. It's a discrete chaotic map. And what you see is characteristic of chaos where you have preferred and forbidden patterns. And so you can actually see in this time series up here, you can see that kind of like little short bit of kind of repeating pattern again and again. It's at irregular intervals, so it's not repeating in a routine way. And so you'll also see in this probability distribution higher peaks of various patterns and also forbidden blank areas. All right, how do we actually diagnose this? So we have a diagnostic called the HC plane. On the x-axis, it's our permutation entropy. It's a normalized Shannon entropy, and it basically says how statistically noisy is this time series. And on the y-axis, we have our complexity, or statistical complexity, which says how many statistically preferred and forbidden patterns are we getting. And so we have different regions of this plane. In the bottom right, we've got stochasticity, so a random noisy time series will be there. We've got regularity and periodicity over here. And in this top region, the area of maximum complexity, we have chaos and other types of complex orbits. And so by plotting things here, we can see what behavior we're getting in a time series. So say we have a tracer particle simulation of a model of a globular cluster where you've got those nice, beautiful rosette orbits because we're looking at a spherical potential. And as you see in this plot right here, we've got all of those stellar orbits that we have here falling on that periodic regularity line in the HC plane. All right, quick pivot to talk about what we're doing now in terms of looking at galaxy evolution. So some of the questions you might ask about the role of chaos and stellar orbits in internal galaxy evolution are these orbital changes associated with any sort of resonance passages? Do these orbits experience episodes of chaos? So do they start as regular orbits, go through a chaotic region, become chaotic, and then go back to being regular? Or do they become chaotic and stay chaotic? And these are questions that we don't actually have answers for right now. So with PECCARY, right now, what I'd showed you with that globular cluster example, we've been looking at a stellar orbit and taking the entire time series and applying PECCARY to calculate those permutation entropy and statistical complexity values. But that just tells us an overall estimate of the entire time series. What if instead we look at chunks and kind of window this method and look at chunks over time of that time series? And maybe we can identify and say, okay, this is regular at one point, it becomes chaotic, and then it goes back to being regular, or so, and so on. So this is all very new, stay tuned. But with that, I will put up my summary and I'll just recap. This is a new method, PECCARY. We've got documentation online, also an archive paper, and we're developing a windowed method for galaxy simulations. And if you're interested in using this for planetary stuff or solar system stuff, come talk to me. Thank you.
very interesting. What do you say are best practices for picking N and L?
So that is an excellent question. I actually have, I can pull up a backup slide. But you have to determine, there are basically a couple different timescales. So you have the natural timescale, which is like an estimated oscillation period of the time series. So for a periodic orbit, it's just the period. For chaos, it's a lot trickier because you don't have an actual time like period for chaos. But one of the things that we did was and this is described more in the archive paper, but we gave recommendations for how to calculate this. So basically, if you look at too large of a sampling interval, too large of an L, chaos can start to look like noise. If you look at too small of an L, you're just getting at those ramping up and down behaviors. And so basically what you want to do is you want to get that maximum complexity. And so there's a region of ratios between the pattern timescale, so that sampling size of the ordinal pattern that you're getting, and the overall like natural timescale or the estimated oscillation period you're getting for the time series. And there's a range of ratios of those that are good to use for L and N. N is 5 is good. There have been a couple, because there's been in some other papers on this where basically the higher N, the more sampling points you have, the better. But then you start running into computation time. And so 5 is a good compromise between being relatively quick and also still having good fidelity of your result.
This is super interesting, Sóley. So is your ultimate plan then to sort of integrate the orbits and the orbital evolution for a given simulated galaxy and correlate what you're seeing, the preponderance of the orbital types with, you mentioned bars or bulge growth or some recent merger or something like that? Is that where you're going?
Yeah, in
ultimately?
essence. So right now I'm just starting to get my hands on a simulation of a collaborator, Jason Hunt, who has a warm barred disk simulation. And so we're going to look at areas of interest and say, okay, you know, when we're seeing these transitional periods, what's actually going on with the individual orbits? And like, are these chaotic orbits and what's happening over time? Are these chaotic orbits and they're going back to being regular? So I think what we're planning on is looking at simulations and zooming in on time periods of interest, if that answers your question. If not, we can maybe talk a little bit more after.
Okay, interest of time, let's thanks over again. And if you spoke just now, please stick around for the picture.
Hello. Hi, I'm Mori. I'm a PhD student at a physics department, and my presentation is about plasma flow in force field magnetospheres to fluid model near pulsars in black holes. This is a collaboration project with my advisor and how does that? Yeah, Alexander Filipov. Okay. All right. So in the universe, there are many spectacular phenomena. Those are maybe black hole jets or high energy cosmic rays. But here, I'm going to focus on the pulsars. And well, pulsars involve very strong magnetic field. As you can see, the magnetic field surrounding the pulsar magnetosphere is 10 to the 12 Gauss. Well, the strongest magnetic field that is available in the lab is something like 10 to the 5 Gauss. So compared to that, you can see that this is many orders of magnitude greater. Okay, well, in the case where the magnetic field or the field is so strong, we can make a great approximation. So in order to see what happens, let's see the stress energy tensor conservation. So I just wrote down the stress energy tensor conservation, but I split the stress energy tensor into the E&M field part and in the matter part. And it is, as I said, the E&M field is so strong. And in this case, the matter part, this contribution is so small that we can just neglect this term altogether. Then we get this condition. Well, this equality is just an identity. You just have to write down the ENM field stress energy tensor, and then you get this condition. And then since the stress energy tensor has to be conserved, this is 0. This condition is called force-free condition because this term is a Lorentz force density. And then the ENM electrodynamics that satisfies this condition is called force-free electrodynamics. Well, force-free electrodynamics is a nonlinear system that only involves the field F. And then as you can see, this is the equation F dot J is given by this. J is just this thing. And then you can see it's very simple. But the thing about this thing, this force-free, is that this is not about a vacuum Maxwell's equation. It describes plasma, but it doesn't involve plasma degrees of freedom at all. It's very simple. This is a force-free simulation result. You need a little bit of some conditions to make sure that this actually works, but basically this is force-free. Okay, and I'm gonna try to emphasize why force-free is so cool. Okay, so presumably everything can be derived from QED. Okay, force-free is electrodynamics, so it should be possible to drive it. There are many paths that we can take. Well, we can start from the kinetic theory or two-fluid theory or MHD or whatever you want. But once you take this limit that the energy is much greater, energy of the field is much greater than the matter, then you get force-free. And then we can take even more exotic path. So we don't even have to start from the kinetic theory or anything like that. We can start from the effective field theory, and then we can still get the force-free. We can take even crazier method. This is a bosonization. That's something that I've been working on with Sam. But even if you take this path, once you take this limit, you get force-free. So what's important is that no matter which theory you start from, as long as you take this limit, you get force-free. So it's very, very, very general. So it's force-free. This is a very important thing. Force-free doesn't care about plasma. It doesn't care about the underlying plasma physics. It's plasma physics without plasma. All right. Even though force-free is great, it's a double-edged sword. I said that force-free doesn't care about plasma, right? But well, it means that it gives us an incredible simplification. But that doesn't tell us a lot about the plasma physics. So this is basically the structure of force-free. All right. So we came up with these two questions. Those are the questions that we addressed in this project. So how do we determine the behavior of plasma and the force-free limit? Can we even do that? And then if so, how do we do that? And also, we want to know how the gap physics, local gap physics affects the global flow of the plasma. This gap physics means this is a region where force-free breaks down. This is basically the region where plasma is produced. So in order to address these questions, we assume two things. We consider two fluid, and also we use this as small mass expansion, assume that the mass of the plasma is much, much smaller than the energy of the fields. And then we did everything like fully analytically. The first thing that we found is basically the reformulation of the already known idea that plasma is stuck to the field line. So when the field is so strong, particles just stuck to the field lines. They just move along the field lines. What that means is that the particle's motion is B direction, magnetic field direction, and time direction. This is a 1+1 dimension of physics. And using the knowledge of differential geometry, we can write the conservation law in 1+1 dimension, and then also equation motion in 1+1 dimension. Here, D, this is a covariant derivative, but this is not a covariant derivative in 4D. This is a covariant derivative on this two-dimensional manifold. All right, and since we were able to write down everything in 2D, we can make use of the special property of 2D physics. Once we assume the symmetry of the system, well, namely, we assume the stationary and an axisymmetric fields. And in this case, we're able to solve the equation. We were able to solve the differential equations, and then we were able to write down those algebraic equations that determine the plasma flow and the density, plasma velocity and density. This is some things, and then there's some constants. Those constants encode the boundary conditions. And then the boundary condition is basically characterized by the gap physics, like how the particles are created. And then once those conditions are given, then we can determine how the plasma moves in the force-free magnetosphere. All right, well, this is a plot. I chose certain analytical solution to the force-free. There's such a thing as Michael monopole solution, which is the analytical solution. And then I gave this lambda is a multiplicity. It basically characterizes how much electrons, how much positrons are in the system compared to electrons and that kind of thing. And then I set the energy of the particles at the surface of the star. And then we were able to plot everything. And then everything is analytical. There's some like interesting features. When, for example, this is a case where, well, when the energy of the particle is created in the gap region is small, then the plasma is unable to feel the magnetosphere. Okay, anyways, so the summary of my research, well, in force-free, I basically show that plasma dynamics is described by physics on the field sheet. Sorry, this field sheet is the two-dimensional manifold that is created by the magnetic field and the time direction. And then we show that the global solutions as a function of gap physics, gap particle, this is a location where particles are generated. And then also show that the all gap conditions, not all gap conditions are consistent with force-free. Okay, yeah, that's it, thank you.
I have a question about that last bullet point there that I might be missing the point of something that you said. So I apologize if this is wrong, but you say not all gap conditions are consistent with FFE.
Yeah.
If a gap condition is not consistent with FFE, is the gap condition wrong or is FFE wrong? Like how should I think about that result?
Yeah, that's a good question.
Or are they both wrong?
Yeah, it could be both wrong. Well, I think that probably what actually happens is that if the gap condition is not consistent, then the global magnetosphere isn't force-free anymore. And then that somehow gives feedback to the gap region.
To push it to be
consistent. Yeah.
Okay.
Yeah, that's what I guess.
Now let's thank Maury again.